we want to solve the boundary value problem for the heat equation. Here's the differential equation. This is the heat equation. And we're doing this on the interval from x equals 0 to 10. And we're doing it forward in time. Now, we are starting with some boundary conditions, right? So at the endpoints of the interval, at x equals 10 and x equals 0 and x equals 10, we're told that the heat is fixed to be 0. And that's true for all time. And when time is 0, so initially, the heat function is given by this. So this is our initial heat distribution, and we want to see how that evolves over time. And the way we're going to solve this problem is by using Fourier series. Okay, so we know that this all boils down to an eigenvalue problem. And the eigenvalue problem that we need to use needs to be the one that matches the boundary conditions that we have. So we were told that the function was equal to 0 on the boundaries, and so that's why I'm using this eigenvalue problem. Okay, so and we know that it has infinitely many positive eigenvalues given by this with these associated eigenfunctions. These are all sine functions. And these are all of the eigenvalues. So that'll give us the solution. When we write down our final solution, it will look like this. Okay? Now what we need to do is we need to pick the bn's. These constants out here need to be chosen so that this guy, when t equals 0, and that'll mean, by the way, this whole term is just equal to 1, so we can just ignore that for a second. We need this series to sum to our original function, the x squared times 10 minus x squared. So we need to get that to happen, and we do that by projecting our function onto these eigenfunctions. And that's exactly what this formula is doing. When I project our function onto an eigenfunction, the projection coefficient is given by this. This is the projection of our initial function onto each one of these for each n. Okay? So this is something we need to compute to solve this problem. So let's start with the denominator. Let's compute what this is going to be. Well, first note what our L is. We're going on the interval 0 to 10, right? So our L is 10. So that is what I need to compute. So what we're going to do is we're going to use Wolfram Alpha, which is a computational engine that you can use on the internet to solve problems like this. And the nice thing about it is you can enter your math problems in natural language here. So I can just type integrate. Now what we want to do is we want to integrate what that said was sine squared of n pi x over L, right, from 0 to 10. Okay, so let's go ahead and see what this gives us. And there it is. So this is the expression that we have. That looks a little ugly, but if you think about it, remember what n is here. N is an integer, right? So sine of 2 pi times an integer is always equal to 0. So this whole thing is gone. So really, what value we got here was just 5. So very simple. The denominator here is just 5, and that's true for all n. All right, so there, we got rid of that. That's just 5. Now we do the top, right? So now we're going to do an integral from 0 to 10 of our function multiplied by these guys. Let's see what we get there. So let's go back to Wolfram Alpha here and ask it to do that. So I'm going to multiply our function, x squared times 10 minus x squared times this guy. Let's integrate that. Let's see what we get. Okay, it's thinking. It's still working. Give it some time. And there we have it. We have an expression for that. Now, this expression looks kind of ugly, right? But again, we can simplify a lot of these because remember, n is an integer. So if you take sine of an integer multiple of pi, you again get 0. So this whole piece over here is just equal to 0. So that piece is gone. What about this piece over here? Well, cosine of pi times n, well, that's either equal to +1 or -1, depending on whether n is even or odd. So this piece over here can just be written as -1 to the n. So that's not that bad. So if I were to simplify all this, we could just write it as, so we got this 200,000 here. And then I have this business. And I have -1 to the n minus 1. And like we said, the whole thing was 0. And then we're dividing by pi to the 5th, n to the 5th. That is the numerator for our expression over here for b. Remember, the denominator was 5, so let's divide all this by 5. So dividing this by 5 would just give me 40,000. So let's cross that out and replace it with 40,000. So these are our bn's. So now we have it. We have our solution, right? We just have to insert this stuff in place of bn, and that will give us the answer. And that was just our coefficient. We're multiplying that by and so that will be the answer. There we go. So I just wanted to show you a picture of what's going on. We can see in the background here a graph of our original function, right? And then as time goes forward, we can see that the heat just kind of dissipates out. And that's why everything just becomes flattened out forward in time. So you can see that from the side, everything, all the heat is just dissipating out.